filter before getting into the continuous valued random variable. Another thing is that there are so many other concepts that we would like to discuss. More than one random variable, two or more random variables. In which case we have to talk about what is called as the joint distribution. In particular, joint probability mass function, joint cumulative distribution function, CDF also, and then marginal distributions, and then conditional PMF, conditional CDF, everything can be talked about. Even you can derive conditional statistical averages like conditional expectation, conditional variance, conditional moment, everything can be talked about. We can also extend the concept of independence of that we discussed for with respect to events, okay, to independence of random variables. Okay, we have to change this focus. So these are all easy to understand in the case of discrete random variable, so that when we migrate to later general random variable, which can be discrete or continuous or joint, then it becomes easy to understand. That's why we would like to spend some time. Let's take a case where we define two random variables. One is x, another is y. X is throwing of a four-sided dice, a fair dice, and this is okay. It need not be fair. Okay, let it be fair or whatever it is. We will not just put that one like this. Then your experiment is has two phases. One, what we do is you throw a die, four-sided die, and then toss a coin, and then look at the outcome of both these experiments in stage 1, stage 2, and together you represent the outcome as the outcome of your combined experiment. So, and then you can define a random variable based on the die, one based on the coin. So the range of values x can take is, and range of values y can take is 0, 1. Then what we can do is we can define what is the probability that I will get the case when x equal to 3 and y is equal to 1, or y is equal to 0 and x equal to 2, and we can talk about those things. Then that is represented by joint probability mass. And how do we denote it? Just like the way we denoted the normal probability mass function, that is P is the letter that is used. And if it were a density function, you will use small f, here P, and as a substitute you put the random variable in capital letters, which we are trying to quantify, and write in small case the value or the realization of that random variable at which you want to find the probability. This is how we do it, which is nothing but probability that x equal to x. This is for a single random variable. So obviously for generalizing it for the joint PMF, we write it as P x comma y of x comma y. And by definition it is probability that x equal to small x, y is equal to small y. So in which case we can define probability that x equal to 3, y equal to 1 is what we would like to probably find it out. So assuming that each one is of course they are both are fair, and the outcome of die, throwing of a die is independent of the tossing of the coin, then it will boil down to the multiplication of the probabilities. So it will be 1 by 4 into 1 by 2, 1 by 8. And how do we denote this PMF? PMF, you will give a list of the probabilities, one per discrete value, the random variable takes. So a list would be okay if there were a single random variable. If there are two random variables, you should have an array. So you can have an array, one for x, another for y. So here you put the values x will take, here you put the values y will take, and fill in the probabilities in this grid. So in this case it will be this is how it will look like. You can extend the concept to many random variables also. So that is the joint probability mass function. You can also define the joint probability distribution. How you will define? But here you will use F only. Capital letter, capital F is the standard way of denoting CDF, whether it is discrete or continuous. So again, f x comma y of small x comma small y defined to be probability that x is less than or equal to x, y is less than or equal to y. So in this case, for example, f x y evaluated at, if you want I can put it, or let's say 3y equal to 1. If you put, so what you have to do is you have to add the various cases. Probability that okay it can be 0 or it can and 0, 1, 0 and so on. All the cases that x is less than or equal to 3, y is less than or equal to 2. So that's all you have to do. So if you look at it, so where all these conditions are met, x can take between 3 and it can take 0 or 1. You have to add up all these things. So that way CDFs can also be defined. Then what we can do is, suppose, see in this case it is a very trivial that both are independent. So if you ask what is the probability mass function of x alone, what you will do, you know it is a die, so you will four-sided die, so you will say 1/4 for all. That way without even doing. Sometimes you don't know whether they are independent, what actual random experiment led to the definition of the random variables and so on. In which case, given the joint PMF, how do you find the individual PMF? Okay, is a question. For example, let me say that I have in a similar way x, y, x taking value 1, 2, 3, 4 and this taking 0, 1. But they are not necessarily independent. I don't even right now get into what experiment led to this definition of the random variables and so on. I want to define a joint PMF which is a valid joint PMF. Which means that, what is it? Incidentally, I have to tell that the rule that we have to see is that P x element of Sx, y element of Sy. By Sy I mean the domain, range of values x. The normalization condition has to be obeyed. So, subjected to this condition, I can always fill a number. For example, 1/16, okay, and then again here 1/16, here 1/16, here 1/16. So, these things are gone. So here I can define 1/8, 1/8. then accordingly 1 by 4, 1 by 4, will it add up to 1? Something like that. Okay, will it add up to 1? 1, 2, 3, 4, 5, 6, 7, 8. And then these two are 8. See? I am not sure, but we can always cook up a value so that they all add up to 1. Okay. So what let me just quickly see. Okay. 16 is not 1. This is 1, 4, 5, 6, 7, 8, 9, 10, 11, 11 plus 15, 16. Yeah, I think so. It's added. So now what we can ask is, what is the probability that x equal to x? This is the probability mass function of XL given the joint PMF of XL. It is nowhere it is told that these are individual experiment being conducted to generate these two random variables and all. No idea about all any of those. Then how do we find? We call this as the marginal PMF. So what it tells is, this is nothing but probability that x equal to x. But what is given is these quantities, xy of x comma y, that is what is being given. What it tells is, I am interested in the probability that a random variable x takes a value small x. Then you are told, how about y? Because I know for jointly, then by this you mean I don't care about the value y takes. You can take any value as long as the random variable x takes the value small x, it's okay. That's the only thing I am looking at, irrespective of the value y takes. That is what we mean by this one. Which means that I should add up all those cases for which x takes this value, y takes any value, that is all. So that can be obtained by summing over all possible values of y in its domain, the joint PMF. So this is how you can obtain the marginal PMF. Similarly, you can also define marginal in a similar manner. You can define. So you will see that here Ex of x. You want to just find out those things. So what is this? This will be accordingly 1 by 16 plus 1 by 8. That is what we will get. Here it will be different. Here it will be incidentally same. Here it will be different. So this PMF is different from what we got here. Clear? So similarly, if you want to get probability y is equal to 1, you have to add up these. So if you add up these things, you will get probability y is equal to these things, you get probability 1. If you want the marginal PDF values of Ix, you have to add up like this. This is how you will do. Now, you can also define expectations. Okay, we will come to that later, but only thing is there is nothing like a joint expectation that is meaningless. You cannot tell what is the probability that the expectation of this. You have to have a function. Something like this has no meaning because what do you do? X comma y you cannot put. Joint expectation that x and x takes a value, y takes a value, that has no meaning. If you have a function of g of x comma y, then that has meaning. Some function g of x comma y. On that you can find an expectation. That function can be just xy or x plus y or x squared plus y, 3y or whatever it is. All these are allowed. So for example, what is x plus y if you want to say? You can just find out. Okay. So you find In this case, it is 1 plus 0, 2 plus, this is 1, 2, 3, 4. Multiply it by the respective probabilities. And then here it will be 2, 3, 4, 5 multiplied by 1 by 8. And that will give you expectation of x plus 2. So those things can be defined of a function of both these random variables. Okay. Yeah. Now we will talk about conditional mass function. Conditional PMF of random variables. You can condition it either by an event or by another random variable. For example, you have a sample space omega and you have defined a real valued function mapping from the sample space to the real line, and that is what you call as the random variable. So what you will do is, for every sample point there will be some mapping like this, and on that random variable is defined, which means that you have to give the probability mass function. It's a discrete one, so Px of x is given, PMF is being given. Now let's consider that there is an event in this sample space. Now you are told that the event has occurred. With this new information, now what is the probability mass function of x? Is what the question is. That is, probability mass function of x given a of x given the random variable, the event. To be more precise, it is probability that x equal to x given that event A has occurred. Then what it means is, now see the range of the random variable x is all those discrete values on the real axis to which the function x maps from the sample space. But now if you have told that event A has occurred, it means only one of the sample points within the event A has occurred. Then the range immediately shrinks to only those points that are mapped from the sample point within A to the real axis. So range changes. Range, instead of telling that the range changes, we can tell that other values will not occur at all. The random variable cannot take any of those values because there is no sample point which will map to those things. Immediately those probabilities of taking the values of x which are not mapped by any sample point within A become 0. So the PMF changes. How about those sample points within A? They are of course mapped to some value. They are still correct and they are in proportion. But the proportionality constant has to be appropriately defined so that this so-called conditional probability mass function is a varied probability mass function. That is sigma x element of Sx. Okay. But even A has occurred. You have to put that restriction. If you want, you can put this one or leave it. Okay. But you have condition. So this should be equal to 1. So what we have to do is by that all these probabilities should add up to 1. To do that, what you have to do, it is, so if you look at this one, it's like A given B can be written as property x equal to x. This is one case, and then intersection A. That is, this condition as well as this condition has to be obeyed. Right from here. By intersection, it means that those values of x, okay, but that lead to this small x, as well as the event A is occurred divided by P of A. So P of A is the normalization factor with which we have to divide all these probabilities so that this becomes a valid P of A. So that is how you condition on an event. It's also other things, also this one. Why it is? Because with element there is also another thing. So if A1 to AN forms a partition, by that what do you mean? A intersection AJ is equal to null set, I not equal to J, union IJ from boundary and AI is equal to sample space. Then you can define property of X given AI. Okay, there is an event A. Not A, yeah. No, A is one of these ones. This is not, let's not look at this. Okay, this is not vector. X. So you can define the conditional probability mass function of X for different of these A1, A2, A3. And then if you want the original PM of X, Px of X, what you have to do is that the union of this one becomes, it's nothing but probability of X equal to X given, this is always, you can always write it in, which is again this, and which means that it is sigma, okay, over probability of X given AI of X over all I. The value of the PMF of all these conditional PMFs, value of a PMF at small x, for all these conditional PMFs, if you add it over all the elements of the partition, you will get the original PFX. This way you can define. One more thing that you can do is look at this one. Suppose you are given this. That is, or you, let's say we will talk about different things. Not like this one. Okay, we will take into this one. What else I want? You can also find conditional expectation. So what you have to do? You have to find the conditional PMF of X given Y is equal to Y, and then take the expectation over X. That is, that's how you can do it. Or, for example, Y is equal to that given value, let us say it is 0, then in this case, then you just look at this alone and take the conditional expectation. That is 1 into 1 over 16 plus 2 into 1 by 4 plus. So this would be the conditional expectation of F. Okay. given y equal to 0. And it will change for different values of y. So for here it will be different. And you can also define conditional expectation of here y given x equal to some quantity. Like that, conditional expectations can also be there. Then let's take a case actually where the random variables are related to each other. Suppose you took two-sided dice and then you define random variables x and y. So there are 16 combinations. Each one of them takes a probability 1/16. Okay? So we can define a joint PM of them. Now you can define a function of two random variables. G of x comma y. This is x, which is outcome of a throw of one throw of a four-sided die, by another throw of a four-sided die, and that joint PM of will be. I will define two functions of x and y. G of x comma y is the max of x comma y. And another function h, which is sum of x comma y, which is nothing but x plus 1. So for reasons then I will call this as G and this as H. Then G can take, which is the maximum. What values it can take? 1, 2, 3, 4. And H, the sum. The values it can take is 2. 1 plus 1, minimum 2 to 8. And if you again join PM if you want to try to arrive at it, so I will do it here. So this is how we have to fill it. Huh?
On max be strictly x greater than y or y greater than
No. Maximum of
I mean
whichever the largest value. Both if x equal to y, then you take that as the max. No, otherwise it is not even defined. You have to define. When you say a function, it has to be a well-defined. You have to resolve that question also. Like this. Here what happens here, you can define and then enter all these PM. Okay? And you can now define the joint yeah, I think it's time location just do this.